In our institute, I'm responsible for energy modeling and estimations. And to be honest, I have the feeling that nowadays there are no energy conferences anymore because we have only the climate-oriented conferences where everyone tends to transform the energy sector in order to decrease CO2 emissions. And of course we also make such researches, such estimates, trying to understand the criteria for Russian climate policy. And in the very beginning, I want to make stress on the fact that currently Russia pays special attention to the goal of launching the economic growth. And that's why any initiative is carefully analyzed for socio-economic consequences, and the national climate policy is no exception. So there is the set of climate-oriented solution. It is wide enough, but the key measures are energy efficiency, electric cars, renewable energy. And we have the complex tool for economy, energy and emissions modeling, and the input-output tables in the center of this tool. There are linkages between I/O tables and energy balance, and we are also creating the unit of technological processes where we describe the technologies in terms of materials and product use. And we use this unit in order to estimate the structural changes in the economy because of the spread of new technologies. So in my presentation, I want to show you how we deal with these climate-oriented topics like energy efficiency, energy cars and renewables. And the first case is energy efficiency. I'm convinced that the energy efficiency is crucial and often underestimated parameter. If we look at any energy model, we will see that it considers the energy consumption as a function of economy and demography. And the energy efficiency is what we additionally put into this function as a multiplier. But efficiency is usually set as exogenous parameter. And we just say, let's assume energy efficiency is improving by 2 or 3%, and that's it. But we should be clear if it's 2% or 3%, because actually each percent of energy efficiency matters. And just one example of that, for instance, decreasing CO2 emissions by 1% in roads currently requires either increase in wind and solar energy use by 70% or improvement in energy efficiency by only 1%. So that's why each percent matters. And of course I may sound boring when I want to count each percent, but I have my reasons, because when some researchers want to, I'm not sure, but I think that when some researchers are trying to build the green scenario with low energy consumption, it is the easiest way for them to make it by setting the optimistic dynamic of energy efficiency. And it is the easiest way because there is almost no responsibility, because many readers just don't notice that for them 2% or 3%, there is no big difference between these levels. And for energy modelers, they don't care about if the economy is able to provide such dynamic of efficiency, such dynamic of investments in order to buy equipment, for example. Well, and I think that we can supply more reasonable point of view on such topic, and that's why our institute investigates the linkages between I/O tables and energy balance in order to model the dynamics of energy efficiency in particular industries. Okay, we have I/O table and we have energy balance. On the first step, we prepare the data for investments, capital stock, and capacity utilization rate. And we also prepare the data of energy consumption to output ratio by industry. We use this parameter as a factor of energy efficiency. How can we get it? We just divide the final energy consumption by the output. So, and then we perform the regression calculations, and the the idea is the high investments, capital stock, capacity utilization rate, the high energy efficiency, and the lower energy consumption to output ratio. And then we also have the matrix of I/O coefficients. Well, we know that this matrix shows the technological structure of the economy, so it makes sense to try to model the I/O coefficients as a function of energy consumption to output ratio, at least for the areas of energy consumption. And of course we can look the calculation, but actually it is under developing yet. And I want to show, but I think the idea is clear. We just want the energy efficiency to depend on the economy. This is our goal. And a few examples. The first case is electricity consumption in manufacture of chemicals. This is the blue line, the actual electricity consumption to output ratio, represented by tons of oil equivalent per 1,000 rubles in constant price. So, and this is the function of capacity utilization rate for this industry. So, the quite good result. And here we can see again the electricity consumption to output ratio, blue line, and the I/O coefficient for this process. Again, a good correlation, so we can model it. And another example, okay, so we just, we're going from here to here and then to I/O coefficients. And another example is electricity consumption in manufacture of ferrous metals. Again, the same situations, but the only difference is that we use the function of capital stock and capacity utilization rate. Again, the good function. The next case is technological shift because of the electric cars spread. Well, what is the idea? We have this key input-output equation. And what will happen in case of e-car spread? First of all, we will see the redistribution of value from manufacture of refined petroleum products to electricity supply in the column of household consumption, as e-cars consume electricity, not gasoline, not diesel. So, but we can model it on the basis of the shifts within the energy balance, and I think it is pretty clear. We just model energy processes and then go to the economy. But if the country produces electric cars, we will also see the changes in technological structure, in the cost structure. And we model it on the basis of the structure of different types of cars' weight. So for instance, the production of traditional ICE car requires mostly the ferrous metals, but electric car is heavier, which means the higher material consumption, and it requires more non-ferrous metal in order to decrease the weight of your car, and also it requires the battery. So, and we can describe it by the redistributions of I.O. coefficients. This is our estimate for Russian case. Changes in I.O. coefficients in case Russia produces only electric cars. They are concentrated in the column manufacture of motor vehicles. So we will see the decrease in diagonal coefficient and decrease in the I.O. coefficient for manufacture of ferrous metals, but we will also see the decrease, and we also will see the increase in I.O. coefficient for manufacture of non-ferrous metals and of electrical equipment. Well, methodology says that the batteries are here, so that's why we have such effect. And when we apply these changes in output coefficients, we can estimate the change in annual output by industry in case Russia produces only electric cars. So we will have redistribution of outputs in all industries, but maybe the most important feature is that, okay, Russia, we cannot produce electric car by ourselves. We need the imports. So this means that we will have a negative impact by import growth, and as we can see, the total impact is negative. And this is the source of our concerns. This is the restriction for Russian economy, and that's why the spread to electric cars can hardly be the effective way for Russian economy. And the third case, renewables. Well, there are two fundamental features of renewables-based electricity generation. First of all, it doesn't require the fuel at the operational stage. And actually for Russia, it is the bad news, because we have our natural gas, and natural gas producers sell the natural gas to power station, and it creates the output, is created incomes, value added. So if we replace the gas-based generation by renewables, we decrease these incomes. And the second feature is that due to the lower energy density and fewer hours of capacity utilization, it takes much more renewables-based capacities to generate the same amount of electricity. And due to the lower unit capacity of renewables, it takes much more materials to produce these capacities. And we need much more, okay, we need additional silicon consumption, metals consumption, electronics consumption in case of solar energy, and we need additional concrete consumption and chemicals and electronics consumption in case of wind energy. This is the estimation changes in output in case Russia replaces natural gas based generation by solar energy. Yes, we will have the additional output because of the additional consumption of ferrous metals, silicon, of electrical equipment, but also we have the negative impacts of import growth, increasing electricity price, and decreasing natural gas consumption for the life cycle period. So, and again, as we can see, the total impact is not positive, unfortunately. Yeah.
The GDP or
output? Output, yes. And the same picture for wind energy. Again, not positive. And to sum up, which is what I just said, few conclusions. First, energy efficiency is one of the CO2 mitigation measures, but it depends on the investments and positive economic activity. We can see it. The second, decreasing imports dependence is crucial for low carbon solutions to be economically effective in Russia. And that's why we conclude that only sustainable and dynamic economic growth is the most effective way of successful energy transformation and CO2 emissions mitigation in Russia. It is quite simple but very important conclusion for us, because the economic growth is not the consequence of climate policy, it is the condition of climate policy implementation. So, this is the condition here. And that's it.
Questions, comments? Talk, please.
The capacity utilization variable, how is that affecting efficiency? What's the rationale? And is it a plus or minus?
Minus, of course, because it is similar to the scale effect. Yeah, the higher capacity utilization rate, the higher efficiency. Yes. And of course, when we make our regression calculations, we want to find the equation with negative sign before this parameter.
More questions?
It's a quick one and rather specific, but the input structure for the renewable energy technologies, if you will, what's the source for that?
You mean this?
Exactly.
What is the source?
Yeah.
Okay, I just can find it maybe on my laptop. But of course, it is our estimations on the basis of some work.
Okay. No, I'm just
European work, if I'm not mistaken. And we used the parameters of existing wind turbines, for example, and solar panels. Yes, and we estimate how much concrete we need to build the solar panels, to put it on the ground.
right. Yeah, I'm just asking because I would be really interested.
Yeah,
in something like that.
there is one interesting thing. Like there are different types of panels, and especially wind turbines, and there are different technologies of creating the wind capacities. So we just estimate the one of them, but we consider it to be the typical technology maybe, but there are a lot of them, and of course for each technology we should have the separate calculations. Yeah. But I think that is a typical situation.
Andrey, tell me please your opinion about electric cars. Is it a low carbon solution without switching to renewables or not?
Okay, I didn't use the slide, and of course I have a slide for this topic. And well, in average, it is a solution. But there are examples of countries where the use of electric cars is not effective in terms of climate policy, at least nowadays. For example, China, Poland, Germany maybe, but I've seen a lot of works about emissions efficiency using electric cars in Germany, and I know that there are different opinions, but when I estimated it, well, my opinion was that it doesn't matter what people use in Germany, because the level of CO2 emissions is almost the same for effective diesel car or for electric car. So, but in average, of course, it helps you to decrease the CO2 emission.
Okay. More question? No question, no comments? Okay, please.
Just for interesting sake, have you got a cost for solar, for wind, natural gas in Russia? Because we've done the same exercise a few years ago, and I would just, for my own sake, see what is the cost for solar, the energy costs, and so on. Have you got it?
The cost, you mean the capital expenditures?
No, the plus operational cost,
Plus-
the cost, per kilowatt hour.
I can say that it depends on the price mechanisms on the electricity markets, and you should know that in Russia we have some kind of special feed-in tariffs for renewables, and it is included in the total price, and it goes to companies who create the renewables capacities. It is, if I'm not mistaken, it is about 100,000 rubles per kilowatt. It means about $1,500 per kilowatt. It is the capex for both for solar energy and for wind energy in Russia. It is the current levels, and we have the special law for supporting the renewables, and these levels of capital expenditures for solar energy and for wind energy, they just written, and they say that if you want to build solar energy station, station, wind power station, your capex should be as it's shown in our table, and it is currently 100,000 rubles, which is $1,500 per kilowatt.
Just for, we've also did the calculation. Now, we've got a lot of coal. So we've got coal power stations. Now, if wind is about 30% more expensive, that's now 5-10 years ago, or 40%, and solar about double. And
Yeah.
we've got a lot of sun.
Yeah, but in our structure of electricity generation, the renewables, less than 1%, and that's why they don't affect the total price too much. It is maybe 5% of the electricity price. This is the feed-in tariff for renewables. Yes. Maybe